Ji, Assalamu alaikum. Today in this lecture, we are going to discuss about the uncertainties actually. The uncertainties are simply the magnitude of error in any physical quantity. So when we say that we will talk about uncertainties, so it means that how much error do we have, right? So how much error do we have in any physical quantity? That tells us about the uncertainty. So here I told about that error is basically some sort of undesired value, right? That is an undesired data. And when we say that is undesired data, we can eliminate it or we can minimize it. There are two types of error. One of them is systematic error, and the second one is your random error. Systematic error is basically that error which is from any instrument, like your zero error, your least count, and all that stuff. And then your random error is actually any error which is due to any unknown source, right? So I can say that this is due to any unknown source. Okay. So when you talk about the least count is basically a main area of your absolute uncertainty. So this is the lowest or smallest reading which can be measured with the help of any instrument, that is called your least count. So if I say that the least count of the system is, or least count of any object is a sort of less, then it would measure very small value. So it is basically some sort of accuracy measuring, accuracy measurement of the instrument. So if we have to measure the physical quantity, like here I have mentioned that if there is a meter rule and that meter rule is going to be used to measure some sort of a physical quantity that is here. Okay, so in that physical quantity, we can say that we could use this meter rod from two sides. And when we are going to use this meter rod twice, it means that it means that that is using your instrument, sorry, it is adding your uncertainty two times in uh, one of your uh, measurement. Okay, so here the least count of different instrument is represented to you. Meter rod, vernier caliper, right? For meter rod it is 0.1 centimeter. For vernier caliper it is 0.01 centimeter. For micrometer it is 0.001 centimeter. For thermometer it is 1 degrees centigrade or 0.5 degrees centigrade, or you can say that is the instrument, I mean voltmeter, that can use 0.1 volt. Okay, ampere. So these are actually the values which are being used. So here I have some types of uncertainties in front of you. There are three main types of uncertainties. One of them is your absolute uncertainty. Okay, the second one is your fractional uncertainty. Okay, this is your absolute uncertainty. This is your fractional uncertainty. Okay, and then this is your percentage uncertainty. Percentage uncertainty, uh, a sort of uncertainty which is an extract of absolute and fraction. So your absolute uncertainty is basically the least count. Then the fractional uncertainty is the least count divided by certain value, right? Whatever we have absolute uncertainty divided by certain value, that gives you a fraction of uncertainty. And then percentage uncertainty is basically that fraction of uncertainty multiplied by 100. Okay, so that is what I wish to explain in a quick review. Then, for example, if we have the readings 50 centimeter, 90 degrees centigrade, 200 kilometer per hour, then these all are the certain values. But along with the uncertainty, these values are having some absolute uncertainties, 50 plus minus 1. Okay, and then you can say then that is 59.0 plus minus 0.1, 200 plus minus 10 kilometer per hour, and so on. So all these values are actually, they are carrying some sort of uncertainties. So when they are carrying uncertainties in their reading, so this is a complete representation of the data. So here I have placed all these values with their uncertainties, and that's it. Now, if I say that I have a value of 59.0 plus minus 0.1, it means that certain value is 59 and absolute value or least count of that system or that instrument is your zero point 0.1 centigrade. So it can be simply written as x plus minus delta x, where x is your certain value and delta x is your uncertain value. So for any calculation or for any number, if I have theta, let's say that is temperature 1, and then I have its value 33.0 plus minus 0.1 degree centigrade, and theta 2 is after some change in temperature, we got that theta 2 is 51.0 plus minus 0.1 degree centigrade, then absolute uncertainties are always added. Simply for your same type of physical quantities, or when your physical quantities are added or subtracted, your absolute uncertainties are always added. Whatever the game is, absolute uncertainties are always added. This is the situation you have to handle with, right? So for difference of temperature, let's say I calculated that the values are, the values are 0 point, sorry, 51.0 minus 33 degrees centigrade, and that will give me a situation over here that is 18 degrees centigrade. So 18 degrees centigrade means that is, just a minute, sorry for inconvenience. Okay, so I was saying that is 18 centimeter, 18 centigrade plus minus 0 0.1. So if I say that uncertainty for value 1 is 0 0.1 and uncertainty for value 2 is also 0 0.1, so overall the uncertainty will be 0 0.2. So this is what we, when we talk about the values of uncertainties, this is our situation. And the number of decimal places must be equal to number of decimal places over here, and this must have, your absolute uncertainty must have one significant figure. So there must be one significant figure in your absolute uncertainty. Okay, now when we say that if same physical quantities are added or subtracted, their absolute uncertainty are always added. Simply their absolute uncertainties are added, right? So you have to keep this with you. In case of different physical quantities, this is very important to know that if we have different physical quantities, okay, different physical quantities like your speed, voltage, and all that stuff, they are definitely different. So when we are having different physical quantities, there is a problem of their, you know, units. So what do? We provide a sort of fraction, or you can say a sort of absolute uncertainty, right? And their absolute uncertainties are then added. What do? We add their absolute uncertainties, right? What do? We add their absolute uncertainties. This is very important thing. Hmm. Sorry, my correction. That absolute uncertainties will not be added directly. What do? We will add their fractional uncertainties. Sorry, I was making a mistake over here, right? So we will add there fractional uncertainties, right? Or percentage uncertainties. So remember this thing. This is very important statement for you. I have highlighted that with certain color, but I believe that it is not visible to you. Now maybe it is. So please consider that. Okay. Then, for example, here are some examples I wish to explain with the help of examples and with past paper questions. For example, I have voltages. The value of voltages is 12 volt plus minus 0.1, and then along with that I have current, that is 0.45 plus minus 0.01. Then what will 0.001 milliampere. Then I interested in resistance. What I want to find out, I'm interested in resistance, right? So resistance and its absolute uncertainty, right? What I want to calculate, resistance and its absolute uncertainty, right? So it means my first task is R and my second task is delta R. So the first thing what you have to keep in mind that you have to use the formula. Okay, you have to use the formula for certain value, and that is your delta v, sorry, vr is equals to v by I. What is that formula for you? That is equals to v by I. So put the certain values after conversion and get your number, that is r is equal to 2.67 exponent 5 ohm. Okay, so don't round off over here. This is very important thing to remember, that don't round off over here. Okay, then we have to consider that R is this much. The new step number two is delta R. Now my calculations are supposed to be shifted to another situation, that is delta R. So in delta R, I will prefer one equation for you all, that generally, what do we have? We have some variables in the uncertainty. For example, in this resistance, I have two variables, V and I. And both of these variables are having one power, they are linear. So I have multiplied that with 1. So delta R by R equals to delta V by V plus delta I by I times 1, because they are not having any power. But if they would have any power, for example, here I have used some other stuff, so we can use the power in terms of multiplication, right? So we can do that. For example, if I say that is, yeah, here is its solution. The delta R by R is equal to delta V by V plus delta I by I. So this was actually one of the master equation for your physical quantity, sorry, absolute uncertainty in the physical quantities. So please consider that equation. So delta R by R is equals to delta V was 0.1 and V was 12. Similarly, delta I was 0.001 and I was 0.045. So here there is another trick for you. No need of conversion. Okay, no need of conversion at all. So if you are converting, no need of that, because at the upper value and lower value, numerator and denominator will be cancelled out by each other. So you got 0.031 delta R by R. So from here, delta R is actually 0.031 times R. So it is, I have put the value of R over here directly, and I got that it is 81 point, sorry, 8158.3 ohm. Till now, you can score 2 marks. From here, there is an additional calculations for you. Sometimes you are asked to calculate percentage uncertainty, right? Percentage uncertainty. So for percentage uncertainty, just switch this. This is your fractional one, 0.01. So fraction is delta R by R, which is basically 0.031 and multiply that with um, the value of 100. Okay, that is multiplied by 100, so you will get that it is delta v by v, that is equals to 0.30, sorry, 0.031 times 100, which is equals to 3.1%. So I have explained that in this system. So come on, here is your final calculation, that is for the last 2 marks. Write your answer in a suitable significant figure. So first, what you have to do, you have to write delta x absolute uncertainty in one significant figure. There is a thumb rule, one significant figure, not more than that, one significant figure, right? So delta r can be equals to, here we have five significant figures, so I have to round it off, or I have to convert this. If I say 1, 2, 3, 4, 5, if I shift this data over here, four decimals, so it is nearest thousands. So I can say that if I write one significant figure, it would be, I have just directly approached to this point, it is actually equals to your 0.8 into 10 to the power 4. So this is the representable answer. So you will represent that in the final answer. So I have shown that in your calculator you have an ENG tab. So use that tab to get power of 10 for easy and convenient way. Then second rule, that decimal place of R or any physical quantity must be same as that of your delta x and delta r. Right? For example, here if I have 2.67, there are two dps in this one. How many decimal places we have? There are two decimal places, but in your absolute uncertainty I have 0.8 into 10 raised power 4. I have one decimal place. So if there is one decimal place, so I have to convert the data. Here I have explained that one decimal place should be, the decimal place of 0.08 must be equal to decimal place of 26.7. So here is the answer. The most appropriate answer is, this is the most appropriate answer. Okay, or most appropriate, that is 26.7 plus minus 0.8 into 10 raised power 4. Or you can write that in whole numbers, 27,000, sorry, 267,000 plus minus 8,000. This is also a number that can be accepted. So this was basically related to your uncertainties. So here is one example. I would like to solve this for you. That question is, this is the question, and that question tells us that a metal wire of length L and its circular cross section area of diameter D, right, and its formula for the volume is given to you, v is equal to pi d square L divided by 4, and the absolute uncertainties are given to you here. In diameter, absolute uncertainty is d 0.38 plus minus 0.01 millimeter, length 25 centimeter, and absolute uncertainty 0.1 centimeter, and then mass is given to you 0.225 plus minus 0.001. So here is, if I say that calculate the density of the metal with absolute uncertainty, I mean delta D, give your answer to a appropriate number of significant figures. So it should be 4 to 5 mark question probably. So first of all, what will you do? You will do in this way, that you have to find volume, right? Volume, for volume formula given to you, pi d square and divided by 4, right? And that's it. You will calculate the volume. In step number 2, you will calculate the density as mass divided by volume. Density will be equal to mass divided by volume. So mass is given to you and density is calculated from 1, right? So By that purpose, or sorry, by that method, you can solve that all, that v is equals to pi d square L divided with this is, and you will get the answer over here. And when you will get answer of volume, you will write it down after calculations. This is a certain value, so I have no need to calculate it over here. Then the next one is your mass calculation. You will put the mass is equal to density times, sorry, you have to calculate density. So density is equal to mass times volume, this calculated answer. Then for delta d divided by d, you will see what are the variables which are having uncertainty over there. So the variables in that are actually in density. Density involves the uncertainty in due to some variables, and those variables are delta m over n because mass have uncertainty, delta L upon L because length have uncertainty, and delta D divided by D because diameter has uncertainty. But the game is only diameter has power 2, so it would be multiplied by 2. Rest all would be written simply. So finally, you will write that delta D divided by D or density divided by density. That would be equals to, you will get a number over here after putting all the values, and that number will be written to one significant figure. And when you are going to write one significant figure to that one, sorry, that is not required over here. That is an absolute fractional uncertainty. So fractional uncertainty will be there, and if you want to multiply